So in this video, we're going to talk about the subsets of the reals, what some of those abbreviations are and how they look, identifying and classifying real numbers. We're going to talk about identifying and evaluating functions and function domains. Okay. Now, set builder notation. Basically, you are going to have a squiggly bracket. You're going to put whatever your variable is, many times x or n, okay? This line here means such that. It follows some rule, so maybe x is greater than 7. So that is some rule. It could be an equation, it could be a inequality, and then you finish off your brackets, okay? So it can be something that follows a rule. You can even say n such that n is a member of, that means element of, the integer, and that it is less than or equal to -2. So this section here where the rule is can have lots of information. Sometimes it's just a listing of the set such that n is in the set, such that n is 1, 2, 3, or 7, whatever that is, okay? So it's just a way for us to classify a set. It's really helpful when it's not a subset of the real numbers, like so if it's some of the integers or the whole numbers or things like that. Now, when it comes to subsets of reals, the real number abbreviation is usually like a capital R, or sometimes you'll see one that has like a double back to it. The abbreviation for rational is Q, irrational is I, integer is Z, whole number is W, and natural number is N. And those are capitalized. And if you were to type them, you would even sometimes see them bolded or kind of it almost looks cursive in a way. Okay. Now, what are these sets? Now, the real numbers are any number on the number line. So we're talking positives, negatives, decimals, nice decimals, funky decimals. Positives, negatives, 0, any of those numbers. If you can put it on the number line somewhere, it's a real number. So what isn't a real number? Well, if it has that I in it, for like an imaginary number. Okay. Now, you kind of want to think about these two things simultaneously, rational and irrational. Either a number is rational or it's irrational. It's one or the other. Rational numbers can be written as a fraction. Sometimes you'll just say it can be written as A over B. Irrational numbers are things like square root of 2, pi, that 3.1415926, E, 2.71828. All these numbers, if you look at their decimals, the decimals don't stop or repeat. So if you were to look at the decimals of a rational number, they are going to stop or repeat, and we can write them all as fractions. You can't write square root of 2 or pi or e as an equivalent, a fraction. If you use 3.14 for pi, it's almost right, but it's not perfect because pi is a decimal value that keeps going and going. They have now calculated pi out to like 1 trillion digits with some supercomputers, and it doesn't repeat, it doesn't stop, it just keeps on going. Now, once you know that a set is a real number and irrational, you're done. You can't go further. So then you talk about, okay, if it's rational, is it any of those things? So if you think about what that looks like, if we draw like a little picture, so let me kind of draw a little picture. If we think as this being the real numbers, okay, so that's the real, let me make that look a little nicer. So if this is the real numbers, We kind of break it into rational, kind of in half, where rational is Q and irrational is I. Once we know it's an I, we're done. But Q's we can even classify even more. The way that you're going to classify it even more is you are going to think about, are they integers? That's our next set. Can those be classified next as whole numbers? And the most specific are counting numbers or natural numbers. So let's look at what those are, okay? So I told you that Z was an integer. That is the set specifically of the negatives, 0, and the positive whole things. Their decimals stop exactly at the units, so they are a whole unit, whether they're positive or negative. Whole numbers include 0 and the positives only. The natural numbers, think about, they sometimes can be called the counting numbers, and that's because of the fact it's like we count. So when you teach a little one to count, you start with 1, and it goes 1, 2, 3. We didn't really add 0 to our number systems until quite some time later on, okay? So those are a specific type of rational number. All of those can be written as rational, just put them over 1. Now they look like a fraction. So, and rational numbers can be positive or negative. It doesn't really specify. As long as you can write them as a fraction, that's all that matters. Now let's practice actually using set builder notation in this example. Okay. So set builder notation, again, we want to call the variable, so we can say n for some number. If you called it n and I called it x, it doesn't matter. And then what's the rule? Well, n is greater than or equal to 8, but n is, let's call it an element of the counting numbers, the natural numbers, okay? You could have just easily call it the integers as well. Any number greater than or equal to 8 in the integers would have been included. So there's lots of ways to write these and still be correct. Now what's great about B is we already have the rule, so we want x's, that's our variable, such that x is less than 7. And you don't really have to specify when it's a subset of the real numbers, because we're assuming it's every number less than 7, but you could say x is an element of the real numbers, if you really wanted to be specific. Now, C is more one that there is a rule, okay? So we want some number n, we'll just call it n, and then we need to make the rule up. So n is 3 times some x, where x comes from the integers. That's the only way it's going to be a perfect multiple of 3. So the x's can be positive one, negative ones. You know, think about if you multiply them by 3, you're going to get a multiple of 3. So that's the most efficient way to write that. There's lots of ways, but that's the way I would think of it, okay? Now, set builder notation is not really super efficient. So if you're following the number line and you're a subset of the reals, then we are going to use interval notation. So that's where this comes into play. This is interval notation. It has to be a subset of the reals, meaning like if you were going to color in part of the number line and you're going to use all the values from like 1 to 7, and you would color in all those decimals in between. That's what a subset of the reals is. And we're going to start out with the bounded ones. The bounded ones, I just think of it, has a clear boundary. If you were to draw this on the number line, we would have a closed dot at A, a closed dot at B, and we would color everything in between. Now, the great thing about interval notation is it follows that. It has a closed bracket at A, a closed bracket at B. Now, the assumption is this is our starting value, this is our finishing value. We're going to include A because it has a bracket on it. We're going to include B because it has a bracket on it. And this just tells me I start here, I end here, and I want everything in between. So the only difference between the first one and the second one is we should have open circles at A and B here and color everything in. Now, how do you designate an open circle? Well, you would have a parenthesis on the A and a parenthesis on the B. The parentheses mean that we are getting super close to that value, but we're not going to be able to stand there. So like, let's say we colored in all the values between 2 and 3, but we had open circles on 2 and 3. That's what I mean. The parenthesis says, I can get really close to 2, but I'm still about 2.001. I can get really close to 3, but I'm at 2.999. Okay. Now, sometimes you have a parenthesis and sometimes you have a bracket. You'll notice on this one we've got an equal to here. So we're going to have a bracket on the A, but there's no equal to here, so put a parenthesis on your B. And the last one is just flip-flopped. Parenthesis on the A, bracket on the B. Now, let's take a look at an unbounded inequality. Now, you know how like when you draw an inequality and you color in one direction or the other? Example, okay, so here's A. X is greater than or equal to A. We're going to close in A, and then we're going to shade to the right. Now, anytime you go to either infinity or negative infinity, we're going to call it, it's an unbounded. There's no boundary, at least on one end. So you have to follow least to greatest order. So our least value is A. I get to include it. We're going to keep going, though, to the right to infinity. This next one, if you were to draw it, this time we want less than or equal to A. So close in A, shade to the left, and so we're going to go from negative infinity to A. Close it in, okay? Now, the only difference between the first two and the second two is like here, sorry, that's not very good, but here we have an open circle at A, so we have a parenthesis, then an infinity. Here we have an open circle at A. Now, we're still going to follow least to greatest order, so we're going to go from negative infinity up to A. I'm sorry, my infinities aren't very good, but there you go. Now, the last one is really how we write the set of all reals, and you just put from negative infinity to positive infinity. That means everything in between. So there's no gap, there's no holes. That is what it is, and there you go. Okay? So that is kind of how we would write an unbounded inequality or an unbounded interval. Now, let's look at some examples. Now, if we want to put these into interval notation, I always like to either draw or picture what I see on the number line. So I would have an open circle at -8, closed in circle at 16, shade in everything in between. So we're going to go a parenthesis on the -8. And let's say what variable we're using. We're using x. That is not an 8. I'm sorry. I wrote an 8, so many infinities a second ago. I just made an okay, that's an 8. So we are almost at 8, but we are allowed to be at 16, so put the bracket on the 16. This one is unbounded because even though we start at 11, we want everything from here over, and we are starting at negative infinity. So if we go there, still x's, we are going from negative infinity up to 11, parenthesis, because 11 doesn't have an equal to. Now, if you look at the second one, we have two intervals, or two inequalities, so we should have two intervals. Let me write down our values. You want to always go least to greatest. Your intervals should be in least to greatest order. So equal to negative 16, shade to the left. That's going to negative infinity. Not equal to 5, but greater than 5. So we're going to the right. That's positive infinity. So our answer here would be two pieces. We're going to go from negative infinity up to negative 16. It gets a bracket. Now just put a little u. U is our symbol for or, meaning it can be in this piece or in this piece. And then you're going to go from 5 to infinity. Infinities always get a parenthesis because we can never really land there, okay? What is a function? A function is, I think of it kind of like a machine where every input, which is usually an x, has exactly one output. Output, which is usually y, or sometimes in function notation f of x. Now we explore that a little more in the next lesson. There is something called the vertical line test, and that it basically says for a function, all vertical lines will only touch it once. So we can say it can only be touched once by any vertical line. Okay, so say functions can only be touched once by any vertical line, okay? So let's look at this example to see what is a function. So every input just gets one output, okay? So if we look at our first one here, the vertical lines only touch it once. So yes, that's a function. Here we can find many vertical lines that hit it twice, so that's a no. Now if you know C is a linear function, it has the name right in it, but if you drew it, we would start up here at 7, go up to over 2, and it's looking something like that. But we can even do the vertical line test if we know that that's a line, and that's also a yes. Now, all types of lines are functions except for vertical ones. That's the only one that doesn't follow that rule. So if it's in y equals mx plus b form, yeah, bam, it is a function. Now, if we look at D, the problem here is this input gave us 3. This input gave us 2. So 1 didn't have the rule that every input has exactly one output. We got 2 different outputs. So when that happens, that's a no. You only have to check that the x's repeat themselves. The y's are allowed to repeat themselves as many times as you want. X's can't, okay? So your homework is on the next page. If I'm going to exclude any, it will say it on the top. Most of yours, I've kind of cut out the exact problems that I want. So remember to always take a picture of your notes. Out of the 10 points for your homework, 2 I will look for and give you 2 points for the notes and 8 points for the actual assignment. You can just take pictures of your paper, and there you go. So thanks so much for watching. Hope that helps you understand that. Have a great day.